Great. Hi, everyone. My name is Shan. Today, me and Nick here, we will be hosting a tutorial on geospatial visualization. The topics will be around visualizing large-scale geospatial data with H3 and HexTile. Our tutorial will be break into two sessions. For the first session, we'll be giving presentations. We will go through some basics around geospatial visualization. Nick will then talk about spatial indexing at H3, spatial tiling and hex tiles. So after the break, we'll be giving the part 2 of our tutorials, which will be a hands-on session. We will work through using Studio to create your maps, build HexTile, and do suitability analysis. So first, let me introduce myself. My name is Shan. I worked in geospatialization for about the past 8 years. My background is in architecture. I studied architecture in undergrad and grad school and decided that I actually like computer science more. So I switched my major into design computation. At that time, I fell in love with visualization. I think it's a great way to combining design and computer science all in one domain. So I spent 5 years at Uber's data visualization team, worked specifically on geospatial visualization, open sourced my library called Kepler GL. And later, based on Kepler GL, I co-founded a company called Unfolded, and it was acquired by Foursquare last year. So that's all the badges I collected throughout my career. So as I said, all my interest is in geospatial visualization, and that leads me to starting talking about maps, because that's a foundation of all our geospatial related design and visualizations. So why is maps something that's key, important part of my entire career, and why is map important? To me, maps make physical space a lot more relevant. I can give you a number with many zeros, like there are 125 million buildings in the United States. The number itself doesn't really ring a bell, but I can show you this map instead, saying that this is a map created with all the 125 million of buildings aggregated into a 1 kilometer cell and highlighted using additive blending. So this map itself versus the numbers shows you how a geospatial representation is a lot more powerful or personal compared to a, code number. So that's why, to me, geospatial visualization is a lot more interesting in abstract visualization. So going into talking about maps are fun, but there are 3 basic attributes about maps that we usually talk about. Without them, we won't be knowing how to actually draw a map. The first is about scale, obviously, because, map is about representing a physical space onto a 2D print. The print can be as big as your screen, or it can be as large as entire wall. So when I'm just showing you this image of a map, it's very hard for you to tell what actually this one is showing without understanding of scale. You can imagine probably this is being one of the paths in your neighborhood park, but in fact, this is actually an array of buildings along a narrow spit of Louisiana Bayou. And the central part is actually the bayou, and then all the little dots spitting from it are the buildings along the bayou. So without the understanding of scale, it's hard for people to actually grasp what the map is about. And when it comes to scale, it is also important to show when we're looking at maps, we compare different maps when we will need to look at it around the same scale, right? This is the same scale of 3 major cities, Boston, Berlin, and Paris. All of them are drawn on the same scale. So you can immediately tell, Paris and Berlin are much bigger downtown area compared to Boston, which is just a little center, Fisk size of space. Without aligning all 3 cities along the same scale, it's hard for anyone to understand exactly, how large of an area you're looking at compared to your daily routine or daily understanding of the cityscape. The second part, a fun part about map is projection. Projection are fun because, projection is about converting a spherical space, which is our Earth, onto a plane surface. There are many different ways of projecting our Earth onto a plane. This animation animating throughout different projection way, and then telling you that, if we think about the Earth as a paper sphere and you need to cut it up and put it onto a plane, how can we do it? There's many different ways of doing it based on different way of projection. But projection is not perfect because there are many different ways of projecting, and there are many trade-offs, right? Our most common projection for our maps that we see are called Mercator projection. This projection significantly distorted the area around the polar side. So that's why Greenland always seems to be a huge area that's larger than Africa. But when you're actually showing the size of Greenland and drag it onto size of Africa, you will see Greenland is actually pretty small in real life. So projection always has distortions, and the many different projection, we are actually just trading what are we distorting. We're either distorting the actual area, or distorting the actual shape, or we're distorting the distance or the directions. Based on the use of a map, many map designers have to pick a projection that gives the least amount of distortion to the characterization of the map that they care about. For example, let's go back to Mercator. The reason Mercator projection is the most common projection we see today is because in 1,000 years ago, when we started drawing map, we used map to actually do global navigation, right? We use a map to sail from continent to continent. That's why Mercator projection is used, because it represents lines of constant course. It preserves the angles of where you're going to the vertical lines on the map. So a navigator on the sailing ship can just take the map out, start it to measuring the angle where they're currently going with these vertical lines on the map, and then match it to its compass to know exactly where the ship is supposed to go. That's why Mercator projection is the most commonly used projection, and it kind of just passed down like that. Again, Mercator projection distorted the shape closer to the poles, but it preserved the angles of the map. This is another example of, to extreme, a projection called Good's homologing projection. This one preserved the actual area of the surface of the continent, but unfortunately, because you need to preserve the actual area of the continent, you need to break the continuous ocean into this, into this watermelon-like pieces. So this is another trade-off, right? If you want to preserve the actual area of the Earth, you use this type of projection, but then you have to break out the continent sphere surface. This is another one of a projection called Fuller-Demaxian map. So this is the one that actually is the foundation of what H3 is based on. This is projecting Earth onto a icosahedron, and then unfolded like these triangle shapes. The beauty of this projection is that you can see that all the continent surface actually perfectly preserved. There's no breakage of it. And then you can put most of the continent onto these triangles where you only have to break the oceans along the edge of the triangles. This one also is a compromise between equal area and conformal. So you relatively preserve the area of the Earth. It also preserves the angle of it as well. There are many projections, so the key point to learn is that each projection is a trade-off between a feature of real world and it can preserve and those it distort. So when we are designing map, we need to know what is the trade-off of the projection we picked and matching it to the purpose of the map we're trying to display. The third aspect of a map, obviously, symbols. We all know symbols because we're in data visualization. Symbols are we use to represent abstract data values with an abstract graph. It is the same with maps. We also use symbols on the maps to show different type of real-world features. We usually use a point to draw GPS as lat longs. Usually these point maps used to draw sensor locations, places, building locations, actual real-world physical space. We also use lines. Lines are usually, we use them to draw segments like trajectory, routes, origin-destination pairs. For polygons, we use it usually to draw building footprints, administration boundaries, geofences. And then the other type of symbol we use is raster. We use raster mainly to show satellite imagery photos. And we also use the last one we use is called grid cells. This one are using aggregating raw events into a discrete grid based on H3 or S3 or S2 or geohash. Now let's go back to the fundamental of symbols and to see how is it evolved throughout the years. So the very first map drawn by John Snow is using symbols. It's famously John Snow's cholera map. This one shows how during the time of cholera outbreak, John Snow was going through each buildings and counting number of people that actually died in that household, and he was able to locate one pump that in the middle of the street that was infested with the virus. He was able to locate a pump by just looking at the aggregated people that actually died near the house near this pump. So this is a very straightforward example of using symbols to actually represent abstract data inputs. The next one we talk about is the scatter plot. Scatter plot is a basic mapping that using points as a basic symbol to represent the geospatial data attributes. And in this type of point map, what we do is that we usually aggregate raw data into this kind of point-based visuals, that each point does not overlap with the other points near around it. This map shows the demographic breakdown of different ethnic groups in San Francisco and New York. So the right area are area that has most of white population, and then the green area, the area has most of I believe Asian population, and then blue are African American population. So using this type of point or scatter plot based map, we can, showing abstract attributes such as a percentage of demographic using this kind of scatter plot map. Another common way of drawing maps is drawing this chloroplast. A chloroplast is a fancy word to say hexagon maps, polygon maps. We see chloroplast a lot of time when we're trying to show election maps because we always like to paint red and blue onto counties that voted. That's why you see chloroplast quite often. But there's a lot of discussion around whether chloroplast is the right way to show number of, especially votes, because chloroplast does not have a way to normalize population. The size of each polygon is only relevant to the area it covers. It is not relevant to any kind of aggregated values that you want to represent. This is an article populated by the New York Times showing that all the people voted in this pink area, they are the same number of votes in the pink area versus the gray, which, this projector doesn't show, unfortunately. But imagine there's a US map by gray, and all of that gray area has the same number of votes versus the pink area combined. This is a way to show you how area usually represented in the chloroplast is very misleading in terms of when you want to show actual number, blue versus red. To solve that, these cartograms are designed to specifically address the fact that we always like to use a real world dimension to draw maps, but we can't avoid of misleading people based on the real world position or size or distance that these elements are. Cartograms are designed so that the geometry on the maps can be distorted based on different metrics, right? So people are trying to distort the US map so the size of each state in this map is relevant to the numbers that they try to represent. So you can squeeze Chicago, make Chicago larger if the number of votes in Chicago is larger. But cartogram is fun to draw, but it's very technical. I haven't seen a really good cartogram algorithm that can quickly run and distort the shape perfectly based on the numbers. But it's a good try. So the last one, we just talked about all the symbols, but most of the real world maps are drawn by combining different symbols. We use different symbols to represent data that are relevant to its shape. In this map, we're showing wind surface flow versus the measurement of actually wind speed from different weather sensor locations. We use these arrow shape to actually representing the direction of the wind, and then using these floating particles to simulate the actual airflow. This is a way we usually do in real-world map design, that we combine different symbols together to represent a whole story. Now, fun about maps, let's actually talking about geospatial data visualization. Geospatial data visualization is a domain that developed on top of map design. We care actually, the added element in here is geospatial data. What is geospatial data? And in real world practice, many times we're not just drawing the static lands and buildings that doesn't move. We're actually collecting data and trying to analyzing a large amount of GPS data that's collected by our phones or satellites. We're trying to use this data to understand actually our physical space, and most importantly, how human moves around this physical space. So movement is what we really want to focus with geospatial data visualization. We want to use different visualization type to understand or to visualizing how humans movement navigating throughout the city. This is a visualization I did when I first started at Uber, showing a day alive of Uber trips that are collecting on the Uber platform. And we use geospatial data and visualization to try to understand how humans or animals move, reside, and navigate the built environment. And all the symbols that we showed before can also be used representing in different type of geospatial visualization. We usually use, scatter plot here to visualizing raw places data. Here in this map, I was drawing all the points of interest or POI data collected on the Foursquare platform. We use this type of 3D hexagons to show a density of events. This is one day of taxi trips happened in New York, extruded by this kind of 3D hexagonal representation. We usually use 3D arcs to show origin destination pairs. We can link raw origin destination data and then draw them in this type of real world 3D arcs type of visualization. This map shows the commute pattern in England and Wales and showing how it's linked a person from its home and then to its work destination. We use this type of path or visualization to show trajectories, right? This is a trajectory map collecting by showing all the global shipping routes based on the data by the Navigation Center for Ecological Analysis and Synthesis. This type of visualization is really fun because instead of showing the actual ocean or the continent border, you can kind of tell it by looking at how this path connects and wraps around Africa, go between the Pacific, and go between the Atlantic. The last one is satellite imagery. This is type of visualization actually visualizing the high-depth imagery that collected by the cameras on the satellites. So these cameras actually has high-depth sensors, meaning that they're not just doing normal RGB 256, 256. They can actually do a much deep, high-depth bit image so that it collects like 2 by the power of 8 or 2 by the power of 12 based on how big the sensor is. Once these high-depth imagery collected, we can use different index, calculate different index based on how do you combine these channels. For example, this map is built using the satellite image collected by the NAIP satellites and then calculate via the MSNVI index. This is an index that specifically can highlighting vegetation or different type of land coverage on the grounds. So by applying this indexing to the color scale, we can highlighting the actual crop fields in Kansas. So the red ones are high vegetation, the green one are low vegetation. And the last but not least, since we're going global, a lot of our platform are collecting data based on a global scale. We usually use this type of 3D hexagon to show density on a global projection. This is the population density projected onto a 7-kilometer hex grid of the entire globe and projected based on counts of population in each cell. I like to do this visualization. This is actually a scatter plot on top of a globe. Each of the points are derived by the carbon dioxide surface concentration. And I project these individual points to cover the entire surface of the globe by using the blue to yellow color scale to show the concentration of carbon dioxide. So to summarize, many of the work have been done to visualize geospatial data. Geospatial data is not just about drawing maps. There are a lot of work to prepare the data, processing it using spatial joining, filter, goodbye, and transform, and then playing around with different visualization type to finally design a map and share with others. So I just want to highlight a little bit with the 5 minutes left to show some of the learnings that we did during the past, I have during the past couple of years, purely using geospatial data to understand movement. There are 3 major challenges in movement data. Most of the data has a time dimension. Most of the data is not a single point, usually has an origin and has a destination. And most of the data are large scale, so we always have to use some kind of discrete grid system to aggregate it and analyzing it. So when it comes to time about movement data, it is very complicated. So an element of time, when we understand it, can be continuous if things happens in a continuous time scale. It could be discrete if your data is actually collecting every 2 or 3 seconds. It could be happen on an interval if all you care is about how the temperature change hour by hour, or how the migration happens month by month. So there are different type of way of processing time, and then our visualization has to be able to handle all different way of time data being collected. That's not just about, time is not just about when, it's also about when, where, and for how long. That's what makes time extremely complicated when it's on top of the normal geospatial visualization that we do. So let's talk about them individually. So continuous time, when does this type of thing usually happens? We usually have to visualize the continuous time in understanding this type of trajectory data. We collect trajectory usually on a seconds or minutes by minutes interval, but in the end, we want to be actually visualize the trajectory as a continuous path. So when we have data like this, what we usually do is that we will actually have to interpolate a path based on these discrete points and create a continuous time scale. And then we draw individual segments on these paths based on the interpolation. That's how you can see this visualization as a more continuous things moving along the line. But behind the scene, the data we create is actually more discrete. We have to do some transformation on these data to visualizing a trajectory like this. Discrete is the most common way when data is collected. For example, these when we're talking about discrete time data, usually is a single event, right? When the person, this is looking at pickup and drop-offs on taxi trips in New York. Each event shows when this pickup happens and where, and another event shows when this drop-off happens and where's. So when we have a discrete time events like that, we usually can just draw a histogram of all the events and kind of just animating through a moving time window. And when we're animating it, what we do behind the scenes actually filtering these individual events by whether they are inside the time window or not. So this is a common practice if you have a discrete type of time. And the third one is time interval. Time interval is relevant when we do spatial temporal analysis. For example, showing how neighborhoods visitation change hour by hour, day by day. In this type of visualization, our data is extreme discrete, but it's discrete binding to an interval. So what we can do is actually for this type of data aggregated by time interval, we can use transitioning colors, size, opacity of a feature by a set interval. This will create kind of a continuous time visualization, make you think that things are actually smooth transitioning between one window to another. But behind the scene, this is actually just showing, a hour by hour events using this smooth transitioning between different visual channels. Second, origin destination. This is the most common data type that we usually collected on, when you try to understand movement data, because it's all about where things start and where do people start, where the trip start and where does it end. When it comes to this type of origin destination, I like to use this type of visualization called brushing. So brushing allow you to, move this type of interaction where you allow you to move your mouse around the map, only highlighting, or OD pairs that near your mouse location. This is a pretty fun interaction that allow you to highlighting areas that you care about. For example, highlighting OD pairs along the airport, highlighting OD pairs along, downtown New York. You can use this type of interaction to filter or to narrow down to a specific area and understand its OD pairs pattern. Now, the OD pairs is fun, but in terms of actually showing aggregated result, is not great. That's why there's this type of flow visualization that is based on top of the OD pair, but apply KD tree aggregation so that it clusters the origin or destination based on the proximity. And then, using the size of circles and narrow arrows or fat arrows to show exactly how many trips are happening between these clusters. So flow on top of, it's actually a much straightforward way if you want to at a glance see where is the hub of your transportation is, or where most of the trip happens. When I turn my raw arc visualization into this flow map, I can immediately tell that a lot of the trips that happens between Chelsea, Midtown in New York, and East Village. So this visualization, even though it's static, but it's actually much statistically much clear for a viewer to show the actual aggregation result. And last but not least, this is actually an introduction to the second talk that Nick gave. Well, it's about a discrete global grid system. So I've been showing many of these type of maps a lot, showing raw scatter plot of raw events and highlighting the density. But usually this visualization is good to, at a glance, sanity check to see where your data is, what the density of it. But if you want to run any spatial analysis like correlation, anomaly detection, clustering, you actually need to start binning these raw events into a spatial unit so you can visualizing each aggregated attributes. For that, after I bin these individual results into this hexagon cells, I can then calculate a certain attributes. For this map, what I'm showing is the average ETA of each trips happens in this cell. I can then immediately see which part of the city had higher ETA, which part of the city has lower ETA. That's a pre-introduction to H3. Nick will give more talk about. H3 is a hexagonal spatial indexing system that you can use to break the world into very fine grain, a meter size, 2 meter size cells, and then calculate different metric based on the aggregated raw events located in each cells. We did many studies. This is an interesting one showing just by breaking trips into each individual cells and then running machine learning models on these cells, we'll be able to cluster the behavior of trips by when does this trip happens during time of day. So we cluster these cells by whether they have most of the activity around nighttime or you have the most activity in the daytime. And then after we be able to run my model to cluster these cells into 5 categories based on their, activity, we can actually paint this map of San Francisco. And purple area, the area that most of the trips happens in the mornings. Green area, most of the trips happens at night. And orange area, most of the trips happens in midday. It's a very fun activity, and then until we actually compare with the zoning map, remember the zoning maps update every 10 years. It does not, it gives you a regulation on what kind of building you can build in this area. So when I color the zoning map kind of just by residential, retail, entertainment, or office, I can kind of see the correlation just based on, on the left side, data collected by raw trips and categorized by ML model. On the right side, 10 years ago, San Francisco Planning Department released this zoning map. And then we can see how the zoning has effect on actual activity of the city. So that's kind of a quick walkthrough. Everything about geospatialization, there's definitely a lot more. I'm happy to answer more questions if there's any. Or we can just go on to Nick. Thank you.
Set up. Hi, my name's Nick Rabinowitz, and I'll be talking to you today about your friend, the hexagon, more specifically talking to you about the H3 grid system and how we made some of the choices that led to it and some of the things you can do with it. So very quick intro for myself. I'm a senior staff engineer at Foursquare. I work there with Shan. I also worked with Shan at Unfolded and Uber, and before that, ClearStory and a variety of nonprofits and NGOs. I've been a software engineer for many years, Spent the last 10 years or so in mapping and data visualization. And I'm currently one of the core maintainers of H3 and the core maintainer of H3JS. Also, I love hexagons. I'm not great with mics. So a quick overview of what I'm going to be speaking about today. I'm going to be talking about grid systems in general and why you might want them, what they're good for, why they're a useful kind of geographic abstraction. I'll talk about the H3 library specifically and what you might use it for. I'll go through some of the gory details of H3. For anyone who's actually a practitioner and meaning to use this, there's some key things to know about it. And I'll go through a little example of how you might use H3 in practice to do a simple analysis. And at the end, I will talk about HexTiles, which is a technology we've built on top of H3 at Foursquare, which uses H3 under the hood to handle very large data sets that would be too large to bring into the browser, since most of our geospatial application is browser-based. So let's start by asking, what is a geographic grid system? We all know that the real world is very messy. There are a lot of things in it. And no matter what we do to work with it, we really have to abstract that mess into simpler forms. Shan went through a variety of geographic data types that we use to do this kind of abstraction. The most common are points and lines and polygons, but still very messy. These things are not particularly accurate. They're not particularly easy to work with. They provide their own edge cases and downsides that can be difficult to work through. And sometimes we find ourselves wishing for a cleaner and more mathematical abstraction. And that's the kind of thing that a geographic grid system provides. So a discrete global grid, where you've broken up the entire globe into roughly equal area cells, is a new kind of abstraction, comparatively new kind of abstraction, that we can apply to the Earth. They divide the world up into these uniform cells, and the big benefit there is that it moves everything into one common unit of analysis. You're no longer dealing with things at massively different scales or even different dimensionality. A point has basically no dimensions compared to a two-dimensional polygon. And they're not biased by many of the natural and human processes that bias the rest of our mapping primitives. And in addition to that, they support a variety of algorithms that are hard to do otherwise. So as I said, one of the benefits here is that it moves it from this sort of messy space into a fairly clean mathematical space where we can perform a lot of transformations and processes that would be difficult to do in with traditional data. To take a couple of comparisons, compared to administrative boundaries, which we often use as a way of bucketing data points, grid systems offer comparable areas, which is almost never true for administrative areas. And they're unbiased by the kind of history, either legislative or political or coming from many other sources that might shape an administrative area. I always think of administrative areas as a polygon that's been produced for someone else's use case. Zip code areas are a good example here. People use zip code areas as a fine-grained kind of geographic area to bin data, but they're actually based on postal delivery routes. And unless you're really interested in postal delivery routes, that's not actually a meaningful thing for you. So it's much better to take something that doesn't have that built-in bias, where the edges aren't necessarily someone else's edges, aren't necessarily something that you have to care about, and use it in your own ways. Compared to ad hoc bins, so anyone who's used GIS software, you can make your own grids in many of these systems, in QGIS or ArcGIS, and you can shape them exactly the way you want, you can align them exactly the way you want, but it's very difficult to share those grids with anyone else. And if you're indexing your data to those grids, that's not really something where you can have a portable identifier. You can't take your grid cell and then send it to someone else and expect that they'll be able to do anything with it. This is especially important when you're building larger scale systems where you want to use these grids to transfer data, to share data, to do interoperable operations between systems. So I've been talking about grid systems and not just grids because most of the grid systems that we use are a set of grids. They're multi-resolution sets. Usually there's a hierarchical relationship between these different grids. And you often have sort of parent-child relationships, so you can walk up and down the grid at different levels of resolution. Some example grid systems that you may be familiar with. Probably the most basic is the graticule, using lines of latitude and longitude as a sort of basic grid to divide the world up. And you can use that for indexing as well by reducing the precision of the latitude and longitude values. But it has a lot of downsides. It's not really built to be a discrete global grid system. It's built for other purposes. And your reduced precision is hard to model in many cases. I can talk more about that later. Web Mercator tiles are another way of uniquely addressing discrete areas of the Earth. And this is commonly used in web mapping, but also has been the basis for things like geohashing. S2 was probably one of the first real purpose-built discrete global grid systems coming out of Google, using quadrilateral cells and a cube-based model of the Earth. And then finally, H3, which is what I'll be mostly talking about, uses a hexagon shape to divide the Earth up. So why would we use hexagons? That's probably the first question most people ask when they see the H3 grid system. There are many shapes that can tile the plane. Why would we choose one over another? Why would we choose hexagons instead of birds and fish? Birds and fish are very nice. They don't make a very good geographic grid system. So what does make a good grid cell? The actual answer for this is the one that fits your use case. But when you're building a system like H3, you really want to cover as wide a variety of use cases as you can. You want to make a general purpose grid. And when you're making a general purpose grid, these are the kinds of things that you have to take into consideration. So the first thing you really care about is uniformity. You want uniform shape, uniform edge length, uniform angles. And the reason why you want uniformity is because the more everything is the same within your grid system, the more you can treat these things equally without having to make special cases for, say, this angle versus this angle on a given right triangle. So already, if we want a regular polygon that tiles the plane, so if we want regular angles, we get a regular polygon. And if we want to tile the plane, we only really have three choices. We have triangles, we have squares, we have hexagons. You also want something that's optimally compact. And there are different ways of thinking about this. I think the easiest way to think about it is if you took a random number of points, you put it within that cell, what's going to have the least margin of error? What's going to have the lowest standard deviation from the center? And the hexagons, you can see visually, but also you can prove mathematically that they're the most compact of these shapes. And because of that, they have much fewer sort of outlier effects around the edge angles than you have, especially in a triangle, but even in a square. You want something that's optimally space filling. So if you're going to be turning 2D shapes, country boundaries or other administrative boundaries or whatever you're trying to model, you want something that's going to do the best job of representing that shape as a set of cells. And while I don't have a mathematical proof for this, in general, hexagons, because of their compactness, are going to be better at this than squares or triangles for cells of approximately the same area. I'll take that as a hint to remind you to put questions on Slido, and I'll be happy to answer them at the end of the talk. I also wanted to mention uniform adjacency. This is really one of the big benefits of using hexagon-based cells. There are a variety of algorithms where you really care about the neighbors of a cell. You're moving from cell to cell, and you want to move to all the neighbors equally in one way or another. One easy example of this is if you're doing data smoothing, you want to smooth out equally in all directions. And hexagons are the clear winner here. All of its neighbors have equal prominence. When you look at squares, and even more so with triangles, you have 3 or 4 perfect neighbors, and then a set of other imperfect neighbors that probably still need to be considered as neighbors, but are not truly adjacent, side adjacent to the cell. And because of that, many of these algorithms have to treat those neighbors differently from the true neighbors that are side adjacent. You also want hierarchical relationships. So you want to be able to assign a set of child cells that fit within the parent cell. And ideally, you want that to be a perfect containment. You want to be able to perfectly aggregate up children to parents. This is one of the places where hexagons make a trade-off. You can see that if you take seven child cells, you can fit them within a hexagon. They're not going to fit perfectly. And so you end up with some area that's inside the parent, some area that's outside the parent. Compared to squares and triangles, this is a little bit worse. But frequently, it's good enough. It depends on your use case. This is probably one of the biggest biggest choice points for someone choosing a grid system about whether you're going to go with something like squares or whether you're going to go with something like hexagons, whether it matters that a parent perfectly contains the child. And finally, you want low shape and low area distortion. And this comes back to the projection that you use for your grid system. Shan touched on this and talked a little bit about how pretty much all projections are going to be doing some amount of distortion with shape and area, and you're usually making some trade-off for those projections. One way to minimize that trade-off is to have more projection surfaces. So the smaller the area of the Earth you're trying to project, the less distortion you'll get. Because of that, most global grids are built on top of a regular polyhedron. These are the available regular polyhedra that we can choose from that have equal shaped faces that use regular polygons as their faces for all the same reasons that you would want regular polygons for your cell. You also would like to have them for your base polyhedron. And you can see that of these choices, the one with the most faces has the smallest area per face. It's going to have the least distortion, and that's going to be really useful to have a low distortion projection. The one with the most faces that we have available here is the icosahedron, and you cannot tile an icosahedron with squares. You can tile it with triangles. You can tile it in some ways with hexagons, as I'll talk about in a moment. But if you're using squares, you really have to choose usually a cube, and sometimes a 8-sided figure I think you can use as well, or simply a cylinder, which is effectively a one-sided surface that many maps are based on, but that has a great deal of distortion, particularly toward the poles. So if we look at all these considerations, hexagons come out ahead in almost all of them. The ones where we fall down a little bit are perfect child containment, as I talked about, and uniform shape, which I'll come back to in a sec. One common comment about hexagons, particularly as a mapping system, are that we just use them because they look cool. And I would argue, especially because we're at a Viz conference and we understand the sort of perceptual nature of visualization, that they look cool because they are cool. When we say that they look cool, what we're effectively saying is that they're more visually comprehensible than some of the other possible shapes. And that the cool look, if you will, is really a way of saying that they're a better representation of your data on a map than a square might be. This is a comparison between S2 cells and H3 cells showing data laid over San Francisco. I think that this is street trees, but I wouldn't swear to it. And you can see that there are places where the hexagon map looks smoother. It has fewer visual artifacts, and it overall represents the data a little bit better than the S2 cells do. So that brings me to the actual H3 library, what we built to create the global hexagon grid that we use. We built this at Uber. It's now an open source project. It's widely used. And we built it by choosing these particular parameters for our grid system. We chose an icosahedron for the base polyhedron for the reasons that I mentioned before, giving us low shape and area distortion. We chose this Dymaxion orientation. So it's a way of orienting the icosahedron on top of the Earth's surface that minimizes vertexes on land area. So you get almost all of the vertexes falling in water, which is great if you're mostly interested in land, which most use cases are. I've had some maritime data analysts yell at me for this choice, but I think by and large it's a more general purpose choice than splitting up land area. It uses hexagons, as we've mentioned many times, for the base cell. It uses a mnemonic projection, which has some trade-offs. There are other projections we could have used on each face of the icosahedron. Mnemonic projections are fast to calculate, and they have a reasonable trade-off between shape and area distortion. You can get perfect equal area cells if you're willing to deal with more shape distortion, but you get much more shape distortion around the corners of the faces of the icosahedron. And then finally, it uses this hierarchical addressing indexing system that allows us to assign a unique identifier to every grid cell in the system. So here's a visual representation of how the grid is constructed. We project this icosahedron on top of the surface of the Earth. We take each face of the icosahedron and break it up into hexagons or semi-hexagons, or in some places, triangles at the corners. And then we subdivide and subdivide and subdivide. So each hexagon gets subdivided into 7 children, and down and down and down. We have 16 different resolutions, down to resolution 15, because we started 0. And so we can go from these almost continent-sized cells at the coarsest level down to under a square meter at the finest. Here's a picture of it laid out across the globe. One of the things I mentioned was the hierarchical indexing system we use. So because every hexagon in the system has 7 children, each of those have 7 children, you can imagine an indexing system where we're basically just giving you the address of the res 0 cell, and then it's res 1 child, 0 through 6, it's res 2 child, 0 through 6, it's res 3 child, etc. And so we can walk down this hierarchy to find the exact cell that we're looking for, even at a fairly fine level. We've stuffed this into a 64-bit integer. That's the H3 index itself. And there are lots of nice things about being able to fit this into 64 bits. One of the nice things is that it's a data type that many languages can deal with. Coming from a JavaScript background, I'm sort of sad that it's 64 bits, but we can also represent it very easily as a hexadecimal string. The hexadecimal string is usually what we use as a data transfer format because it's the most portable. But using it as a 64-bit integer allows a lot of bit operations that can be very fast and allow you to manipulate cells across the grid in an easy way. So talking about the library itself, you can see more at h3geo.org. The library is open source. It has a fairly large user community. I don't know if I can say for certain that it's the most widely used discrete global grid at present, but I think we're probably close. S2 may still have more users. It really depends. It's built in C, and there were various reasons of doing that. First, because it was very fast and very portable, but also because then you can make it available to many other languages through bindings. So we have bindings for Python and Java and JavaScript, but there are many other contributed community bindings as well for Ruby and Scala and a wide variety of languages. We also have community-supported bindings for database systems so that you can use these functions directly in SQL. So Postgres and BigQuery and I think Snowflake now, and we're working on Presto. So there's a variety of database support as well. The kinds of core functions that are covered in the library, we obviously have indexing. So the ability to take a point and tell you what cell it's in, and do the reverse. Take the cell and tell you what its geographic coordinates are. We can also do a lot of hierarchical traversal, so we can go from cell to parent or from cell to children. We can do grid traversal, so go from cell to neighbors or find a path between 2 cells. We can take regions, so we can transform a polygon to a set of cells using usually center inclusion, but there's a variety of different ways you can do this. And we can go from cells to polygons, so to take the outline of a set as a polygon. And there's a variety of other functions as well. So pretty much everything you would want to do with a grid, maybe not quite everything since we have a long list of things we still want to add to the library, but many of the things you'd want to do with a grid are available directly within the library. I don't think I have time to actually play around with this in this talk, but I'd encourage you to go here if you want a quick hands-on view of how to use this. This is using the JavaScript library in order to do a very easy tutorial where you can just change values on the fly and see the results. There's a set of notebooks I put up here that cover different kinds of transformations you might want to do and different kinds of approaches that you might start with when using H3. I did want to get into some gory details. There's a few things that you can't avoid when using a hexagon library, and there's a few things that we couldn't avoid when building a hexagon library, let's put it that way. The first one is pentagons. So if you're familiar with an icosahedron, you can see that you have these 5 edges coming together at every icosahedron vertex. And because of that, you can't really put a hexagon there. There's no way to turn that set of triangles into a hexagon. You can only turn it into a pentagon. So the bad news is that every resolution of H3, there are 12 pentagons that you need to deal with. The good news is that there are only 12 at every resolution. And what this means is if you're doing res 0 analysis, where you're dealing with 122 very, very large cells, this might be something you really have to consider. If you're doing resolution 9 or 10 analysis and you're on land, you're probably never going to hit a pentagon. So most of the time, I would say that people consuming the H3 library don't need to deal with pentagons. I would also say that probably 60 to 80% of the code in the H3 library is dealing with the pentagon cases separately from the hexagon cases. So hopefully we've covered a lot of that so that you don't have to. But it does affect the assumptions you can make about what you have in the library. So you can't really make assumptions that you always have 6 neighbors. Sometimes you have 5 neighbors. You can't make assumptions that you always have a given number of vertexes, for example. There is area variation across the grid. This gets up to just about 2x, almost 2 times area variation in every resolution, particularly when you consider the pentagons that are smaller than hexagons by about 1/6. And again, that's part of a trade-off that we made, area variation versus area distortion versus shape distortion. So, we made a trade-off that took a compromise there, and because of that, you're not always going to have actual equal area cells. I think technically this means that we're not a true discrete global grid as per at least one of the specific definitions of that. But in practice, particularly within local areas, you can truly treat them as equal area. If you're doing a global analysis, you might have to consider that not all of your cells are going to be exactly the same area. As we discussed before, you also have this issue of child non-containment, so we don't perfectly contain our children. And this is an issue when you are aggregating up or dispersing data down. You can't perfectly move data up from the children into the parent without some margin of error. Again, the good news here is that the margin of error is fixed no matter how far you go up. So you can see that you've got a certain margin of error going down 1 resolution. It's about the same as the margin of error. I think it's exactly the same as the margin of error going down 2 resolutions or 3 resolutions. But as you go down to 3 resolutions, you have cells where the entire area is outside the parent. So you do have to consider this when you're aggregating particularly, or when you're trying to subdivide a parent into its children, that you get this, this convoluted edge rather than an exact edge that follows the parent. And finally, I wanted to mention H3v4 versus H3v3 because we released H3v4 maybe a month and a half or 2 months ago. And one of the decisions we made, which I think overall will prove to be a good decision, but is not the kind of thing that developers thank you for, was the decision to change almost all of the function names. So many of the function names have changed. The main reason for this change was clarity and consistency because we had a lot of confusion with users with our older function names. But keep in mind that when you see H3 code, you may be looking at H3v3 function names and have to map them to H3v4. The recommendation is to use v4 if at all possible, which it should be unless you have to work with a legacy, with something that's using the legacy version. So I wanted to go through fairly quickly an example of using H3 in practice, just so you can get a sort of more visceral sense of what it is to use a discrete global grid library. So this is a point data set of incidents of crime in Oakland. And you might want to know a lot of things about this that are very difficult to see from the points themselves. So sometimes you get a lot of information by looking at a point scatter plot, and sometimes you really need to bin. So usually the first thing that I do when I'm working with a point data set in H3 is to bin each point at some given resolution. Here we've been to resolution 9, and you can aggregate that by count, and then you quickly get this sort of density plot of these incidents over the area of the city. It might seem that that was too coarse, and so you can choose to re-aggregate to resolution 10. You want to find the resolution that makes sense for your use case. Sometimes that's driven by other data sources you need to integrate with. Sometimes it's driven by other kinds of things you need to consider in your analysis. Sometimes it's just driven by compute power that you have available, where you need to take something coarser rather than something finer because you don't necessarily have the compute power to deal with the larger and more granular data set. So when we take counts like this, as everyone knows, many times, taking counts of some human-generated data over some area is actually just a proxy for population, and you're really looking at a population map. One of the really nice things about H3 is the ability it gives you to bring different kinds of data sets together easily and then do math on top of those across those two data sets. So in this case, we put together a separate data set for population. We started with block group polygons. We found the set of H3 indexes for every one of those polygons. We disaggregated the census counts into cells. In fact, when we did this, we also leveraged building data sets, so you could figure out roughly which areas of the underlying polygon actually were populated and which were not. And we come up with this population surface that we can use in other kinds of analyses. So here, we can very easily stick the population data set onto our binned crime data set, and we can perform cell arithmetic across that row. We can normalize crime by population, and that gives you a different view of the distribution of crime within the city. You can see that there's a large red area kind of in the middle of the city that turns out to just be a high population area rather than a high crime area. So being able to do this kind of arithmetic, you might be familiar with this as raster arithmetic if you've ever used raster data. But in this case, you don't have to normalize your raster cells or join them with anything else. Everything's already on the same unit of analysis. So in the last 5 or so minutes remaining to me, I want to talk about HexTiles. So everything I've talked to now up to date has been open source. HexTiles are something we developed at Foursquare. We would like to open source parts of this in the future, but we haven't done so yet. So the H3 grid, as I've mentioned, it gives us this global standard grid system that we can use to partition data. You can use it for visualization, but you can also use it for a variety of technical purposes, like partitioning data for storage or parallelized processing. One of the things it's really good for is using it for tiling. So you can break up your data into these larger tiles. You've got a coarse tile resolution, which defines essentially the partitions of your data, and then the fine data resolution that defines your actual rows when you're thinking about this as a data table. So effectively, each tile is a data table that's been indexed to the data resolution. And we can create these tiles, store them separately on a server, and serve them up as this multi-resolution tile pyramid. So if you're used to map tiles, you might be familiar with the idea of a tile pyramid where you have a small number of tiles at the top at a coarse resolution. As you zoom in, you draw from the larger and larger pool of tiles at a fine resolution. We can do the same thing for H3 data using HexTiles. Why would you want to use this? Well, it's addressing some of these pain points that are quite difficult often in geospatial analysis. The first is to support large data sets, and whatever, we've all had the discussion about what big data is. Whatever a large data set is something that you can't easily deal with otherwise. I think in our case, in the case that we usually work with at Foursquare and that I've worked with a great deal as someone who is mostly working in the web browser, the real question is, what can you actually bring into the browser and process there? Now that window has been expanding greatly, and we can now bring millions and millions of points into the browser, but there's always going to be a limit. You're always going to be constrained by what you can actually do in the user's client. So being able to support large data sets, break them up, and to me as an engineer, what I really like is the idea that you're only using the data you care about. You're only bringing the data into the browser that really needs to be there. You're keeping the rest of the data on the system at rest where it's easy and cheap to deal with. And then you can bring that in, on demand in a way that's very fast and work with it in the browser. It allows you to bring all these things together. That's really a function of the fact that it's built on H3. So, having all these tiles that are already pre-built at different resolutions gives you basically an out-of-the-box join key for anything you want to join. And it means that you can take effectively gigabyte data sets or multi-gigabyte data sets, and you can join them on the fly in the browser just by joining tile to tile. And that gives you this very easy and fluid way of working with extremely large data sets where the end user can basically do fast exploratory analysis, and you don't have to do any major processing on the back end. All of the processing happens offline ahead of time when you build the tile set. So it allows you to do this visual exploration at interactive speeds that would be very difficult if you had to actually do the processing every single time. We can also handle temporal data. I don't know if I have a slide for this later, but you can extend this as it's basically just a data table. You can extend that concept to include a temporal dimension in that data as well. That allows you to do things like animate over time or do temporal joins as well as geographic joins. So you might be familiar with other kinds of tiling systems. The most common are raster tiles and vector tiles. And I think it's worthwhile doing a comparison here. Raster tiles tend to give you a very efficient encoding of data, and they leverage a lot of what we know about image processing and dealing with images on the web. They're very good for representing ground truth sensing data because that's the format it comes in, or it's very close to the format it comes in. But joins can be very challenging, especially if you're joining to other kinds of geographic data. Vector tiles have very precise geometry. You can have very fine-grained geometry. You can represent things like polygons with great accuracy. You can bring these in very easily if you want to draw a map for an end user. So it's really good for something like navigation or administration, where you want to bring in a map, draw it exactly, and then present it to the user. But many kinds of data analysis can be very challenging. So doing joins or other kinds of spatial operations on polygons, it's a well understood problem, but it's not a cheap one. It's a very expensive one and sometimes needs specialized systems. Whereas HexTiles, because we have this standardized geometry, we can use the tile data basically as a data table for a wide variety of analytical functions. And as I've mentioned several times, joins are extremely easy to do. They basically just happen on the fly. You're sort of sticking these tables that already have the same index together. Finally, I want to mention temporal data. So we have the ability to also encode time along with the spatial dimension. And that gives you the opportunity to start working with temporal data sets that might be hard to model in other kinds of geographic data formats. So, for example, if you have a polygon data set that also has temporal data and those polygons change over time, doing things like interpolation can be very difficult. And knowing that that interpolation is correct can be very difficult. If you have point data sets that change over time, you usually have to bin them very tightly. You have points that disappear and reappear rather than points that move smoothly from one place to another. So finding interstitial values can be very difficult. With hexagons, you're basically interpolating one value from one spot to another, and it usually is a much simpler problem. I want to do a very brief demo in the time I have left, mostly because I think that it's a lot more fun to look at this than to talk about it. Let me bring up the US buildings map. So we've talked a little bit about building footprints, and I should have tested the speed of the Wi-Fi before trying this. It's fairly fast, but it still puts a certain onus on the browser. So this data set is built from footprints of US buildings, and we've basically broken up the entire world into very fine-grained tiles, and at the very lowest level, we've said yes or no, does this tile contain a building? Is there a building that intersects with this tile? And then we've aggregated that up so you can count the number of extremely small hexagons that contain a building, and we get this overall map of building density. And the great thing about HexTiles is this multi-resolution approach. So we start with a fairly coarse resolution, but as you zoom in, you can get finer and finer data granularity. This is taking more time than I would wish. Give it a sec. It's coming. There we go. A little bit of data coming in. You can see as we come in, we get finer and finer data, and that can give us a really fine-grained view of data, even when we zoom in really far. When we get all the way in, we can actually bring in data where you can see the buildings themselves. And maybe I should have chosen a slightly less intensive data set for this Wi-Fi system. But But in any case, you can understand the concept here, which is that we've got different levels of resolution providing different levels of data in our application. And as we zoom in, we can get a different view of the data. And as we zoom out, we can get a coarse overall view. So it gives you this idea of overview and details on demand that can be extremely useful when doing exploratory data analysis. I'll stop there before it brings in the data. And I think I will stop the talk there. Thank you very much for your time, and I'm happy to take any questions you might have on Slido, or possibly in the room if no one's asked questions on Slido. So I don't see anything on Slido yet, but if people have questions in the room, feel free to ask them. I believe that there's a mic back there so that people on Zoom can also hear.
Hi. My question is, have you used this for a use case which is not for data that is not on a globe but is on a more planar surface, the hex tree grid? Can it be used for just data on a flat plane, for example?
That's not on the globe. So this is specifically a geographic system. You could potentially use it on other spheres and other planets. We've had that question come up. But it's not really well suited for a standardized hexagon grid. There are systems that can build a hexagon grid on a plane very easily. And in fact, generally speaking, the math for that is much simpler. But you can't really adapt H3 to that directly. H3 is much more purpose-built for doing geographic analysis.
Okay, thank you.
Any other questions? In that case, I'll give you 3 minutes back. Thank you so much for your time.
For over 131 years, the University of Oklahoma has been making an impact. It is a legacy of excellence, a legacy defined by courage and determination, a legacy of champions, both on and off the field. And we're not done yet. From big wins to bigger discoveries, we're advancing Oklahoma, the nation, and the world. Because at the University of Oklahoma, we change lives.
Hello, my name is Peter Wonka, and I will present an overview of the Visual Computing Center at KAUST, also called VCC. The VCC currently has 9 faculty members who publish academic research in the areas of computer vision, computer graphics, visualization, and machine learning. We strive for academic excellence, as evidenced by high rankings from websites, such as CS Rankings, that track publications in the best conferences in different subject areas. VCC research is supported by various core labs. The KAUST Supercomputing Laboratory provides access to supercomputing and a GPU cluster. The Visualization Core Lab maintains visualization facilities and VR equipment. Computational imaging is supported through devices for industrial tomography, microscopy, or cryo-EM. Now, let me show you around at our center. The Visual Computing Center is located in one of 5 research buildings that houses faculty from computer science, mathematics, and electrical engineering. The research buildings are connected by a major walkway, the spine. Along the spine are various shops selling items to support the daily research activities. Most importantly, coffee. Now, we're entering the building on the 2nd floor, where the VCC is located. We are flying around to take a look at the arrangement of offices and cubicles where staff, students, postdocs, research scientists, and faculty work. The posters on the hallway highlight successful research projects from the past. Several meeting rooms can be used for group meetings, lectures, or project discussions. Our faculty teach a wide range of courses in visual computing. Due to the excellent professor-student ratio at KAUST, some specialized courses can even be taught in faculty offices. Our research can also directly be applied to such a video stream, for instance, for activity recognition. Or depth estimation. One part of the VCC is dedicated to the Computational Imaging Lab, which allows for optical setups and the development of combined optical and computational imaging systems. VCC facilities are directly adjacent to facilities of the Visualization Core Lab. For example, the Next Cave. And the large display wall shown here. we would like to highlight the VCC startup company FalconViz that took the drone footage for this video. This concludes our presentation of the VCC. Our members thank you for stopping by and visiting with us. We hope to welcome you in person in the future.
From desktops to data centers, CompuServe to the cloud, the orderly march of progress. Yeah, no. Progress only looks orderly after it's happened. Before it's happened, it's problem after problem after whose idea was this anyway? Unworkable, unfeasible, impractical, impossible. But then you put your head down and you work the problem until answers emerge. New solutions that power you through the next problem, and the next one, and the next one, and the next one, until you get to greener buildings, cleaner cars, smarter factories, bigger blockbusters, interplanetary landers, walking cars. 4 decades of solutions. But it's always been about one thing: finding new ways past whatever problem stands in our way. And we're restless to do more. And that's why we love problems. Because we know when you combine the right solutions, when you merge fields, and converge the technologies no one else can, what's wrong with right now can become what's better about what's next. It's about opportunities, not obstacles. It's about unleashing your talent, not restraining it. It's about unlocking insights in your data. It's about making the things that actually make the world a better place. So let's get out there and do just that. Let's blur boundaries. Let's reinvent rules. Let's redraw the lines that define your talent, your business, your entire ecosystem. Let's go do what doers love to do. Let's not wait for progress. Let's make it. Autodesk it.
For over 131 years, the University of Oklahoma has been making an impact. It is a legacy of excellence, a legacy defined by courage and determination, a legacy of champions, both on and off the field. And we're not done yet. From big wins to bigger discoveries, we're advancing Oklahoma, the nation, and the world. Because at the University of Oklahoma, we change lives.
Hello, my name is Peter Wonka, and I will present an overview of the Visual Computing Center at KAUST, also called VCC. The VCC currently has 9 faculty members who publish academic research in the areas of computer vision, computer graphics, visualization, and machine learning. We strive for academic excellence, as evidenced by high rankings from websites, such as CS Rankings, that track publications in the best conferences in different subject areas. VCC research is supported by various core labs. The KAUST Supercomputing Laboratory provides access to supercomputing and a GPU cluster. The Visualization Core Lab maintains visualization facilities and VR equipment. Computational imaging is supported through devices for industrial tomography, microscopy, or cryo-EM. Now, let me show you around at our center. The Visual Computing Center is located in one of 5 research buildings that houses faculty from computer science, mathematics, and electrical engineering. The research buildings are connected by a major walkway, the spine. Along the spine are various shops selling items to support the daily research activities. Most importantly, coffee. Now, we're entering the building on the 2nd floor, where the VCC is located. We are flying around to take a look at the arrangement of offices and cubicles where staff, students, postdocs, research scientists, and faculty work. The posters on the hallway highlight successful research projects from the past. Several meeting rooms can be used for group meetings, lectures, or project discussions. Our faculty teach a wide range of courses in visual computing. Due to the excellent professor-student ratio at KAUST, some specialized courses can even be taught in faculty offices. Our research can also directly be applied to such a video stream, for instance, for activity recognition. Or depth estimation. One part of the VCC is dedicated to the Computational Imaging Lab, which allows for optical setups and the development of combined optical and computational imaging systems. VCC facilities are directly adjacent to facilities of the Visualization Core Lab. For example, the Next Cave. And the large display wall shown here. We will would like to highlight the VCC startup company FalconViz that took the drone footage for this video. This concludes our presentation of the VCC. Our members thank you for stopping by and visiting with us. We hope to welcome you in person in the future.
From desktops to data centers, CompuServe to the cloud, the orderly march of progress. Yeah, no. Progress only looks orderly after it's happened. Before it's happened, it's problem after whose idea was this anyway? Unworkable, unfeasible, impractical, impossible. But then you put your head down and you work the problem until answers emerge. New solutions that power you through the next problem, and the next one, and the next one, and the next one, until you get to greener buildings, cleaner cars, smarter factories, bigger blockbusters, interplanetary landers, walking cars. 4 decades of solutions. But it's always been about one thing: finding new ways past whatever problem stands in our way. And we're restless to do more. And that's why we love problems. Because we know when you combine the right solutions, when you merge fields, and converge the technologies no one else can, what's wrong with right now can become what's better about what's next. It's about opportunities, not obstacles. It's about unleashing your talent, not restraining it. It's about unlocking insights in your data. It's about making the things that actually make the world a better place. So let's get out there and do just that. Let's blur boundaries. Let's reinvent rules. Let's redraw the lines that define your talent, your business, your entire ecosystem. Let's go do what doers love to do. Let's not wait for progress. Let's make it. Autodesk it.